This is our final lecture on reactive process material balances. And what we are going to consider in this is combustion reactions. And the one new thing that you're going to learn about is calculating the theoretical air and the excess air. Combustion involves oxidation to CO2, okay? And typically there's also water. This happens when we burn fuel, and it also happens when we eat. This is our own combustion that we do in our body with glucose and oxygen, and we make CO2 and water, and we also generate adenosine triphosphate so that we have energy. Similarly, we can combust fuel such as methane. This is methane, not methanol, but we can combust methanol. But this methane can be combusted to CO2 and H2O. So this is the thing that you have to learn, and it takes students, for somewhat odd reason, I'll be repeating this really very simple concept 20 times, and I don't really know how to get it across more clearly, but you're the ones that have to embrace it. And the message here is that we calculate theoretical air in combustion reactions, and this really only applies to combustion reactions. So we're combusting a fuel that with oxygen, and so in these reactions we assume that all carbon goes to CO2, all hydrogen goes to water, all nitrogen goes to NO2, and all sulfur goes to SO2. So the point is here that we typically burn fuel with excess air because we want to prevent that we send fuel off uncombusted. So when we calculate the theoretical air, you follow this formula. You can write it down, you can memorize it if you want to, you can put it on a little cheat sheet, you can put a little tab in your reader so that you come to this formula, because this is what we do to calculate theoretical air. Okay? The moles of oxygen theoretical is the number of moles of carbon in the fuel times 1 mole of O2 per mole of C. The number of moles of hydrogen in the fuel. Okay, what are we talking about here? Let's say we have let's use methanol, CH3OH. Okay, so we have 4 moles of hydrogen. So we put 4 in here for H. 4 moles of hydrogen, okay, and we multiply by 0.25 moles of O2 consumed per mole of H. Now you're going to say, why? You should look at the formula, the combustion formula, to go from methanol or from methane or anything, and you will see that for every mole of hydrogen in the fuel, 0.25 moles of O2 are consumed per mole of H consumed. Okay, and then if we happen to have nitrogen in the fuel, such as when we have a protein, sometimes you can burn proteins. It's actually good for your metabolism. So when you combust nitrogen, then you consume 1 mole of O2 for every mole of N that's actually in the fuel. And I'm not talking about N2, okay? N2 is not the fuel. It's if we had a protein that has, say, C4H7O2N, okay? A typical biomass. Biomass is used as a fuel. So you have a nitrogen in the actual fuel. Okay, so there's going to be 1 mole of O2 consumed per mole of nitrogen in the fuel. And the same would hold true if you have sulfur in the fuel. Now, if you have oxygen, in the fuel, such as we have here with methanol, you subtract 0.5 moles of O2 per mole of O consumed. Okay, why? Because here we actually, the oxygen is not going to be consumed in the sense of the fuel. It's actually going to combine with the carbon and the hydrogen. So for that reason we subtract the number of moles according to this relationship. And that gives us the number of moles of theoretical O2. So we calculate the theoretical O2 according to that equation, and then we calculate the excess O2 from percent excess is equal to the actual O2 fed minus the theoretical O2 that you calculated with that equation divided by the theoretical. And this is going to also be the same thing when you look at air. Okay, the percent excess air is equal to the percent excess O2. Why? Because the nitrogen in the air doesn't burn. So let's do an example calculation. We'll combust methane with 30% excess air. Determine the composition of the product assuming complete combustion. Okay, that means there's no carbon monoxide. Okay, can you remember this? Complete combustion means no carbon monoxide. Okay, no CO. Complete combustion. And 100% conversion of methane, which means there's no methane in the product. All right, so here's our relationship. We know the formula. The chemical reaction for methane is, let me just see if I put it here. No, I didn't. Okay, so CH4 plus 2O2 goes to CO2 plus 2H2O. This is our chemical reaction. So now we can write our relationships here. We need N of air. We can calculate that directly because we know that we have 30% excess air and we have 1 mole per second of methane. Okay, then we have here 4 products. Why is there oxygen in the product? Because we have excess air. For the same reason, not for the same reason, but we have the nitrogen in here, the nitrogen out is going to equal the nitrogen in. So as soon as we calculate our N of air using the excess air that we're given here, then we can calculate the moles of nitrogen in the output because it'll be the same as what's going in. So let's look at the degree of freedom analysis. We have 5 unknowns on the flow chart. N of air, N of N2, N of O2, N of CO2, and N of H2O. And when you do your degree of freedom analysis on the midterms, you must write out which are the unknowns that you're talking about. -3 independent atomic species balances. You should also write those: carbon, hydrogen, oxygen. -1 molecular balance on independent inert species. And we have one additional relation between unknowns, and that is that we know what the excess air percent is. So with this we have 0 degrees of freedom. So first we calculate the theoretical oxygen. 1 mole of carbon times 1 mole of O2 per mole of C plus 4 moles of H, CH4, okay, times 0.2 moles of O2 per mole of H, and that gives us 2 moles of O2. Okay, so now we're going to calculate the actual oxygen fed, and we know it's 30% excess, so we're simply going to multiply the theoretical times 1.3. Okay, 30%, we're talking about excess, so that means 1.3. And that gives us 2.6 moles of O2 per second. Now we can calculate the moles of nitrogen fed. We have 2.6 moles of O2 times 79 moles of nitrogen per 21 moles of oxygen. And I invite you to just calculate what is that ratio, 0.79 divided by 0.21, and see what that number is. Okay, I think you'll find that it is 3.76. Okay, and that is going to equal 9.78 moles of N2 per second. That's the moles of N2 coming out, as well as going in. So our total moles of air, N air, is going to be 12.4 moles per second. Now we do a carbon balance. Carbon in is equal to carbon out. N of CO2 is equal to N of CH4. Done. Now if we do the hydrogen balance, we have moles of hydrogen out is equal to moles of hydrogen in. 2 times N of H2, since we have two hydrogens in each water, is equal to 4N of CH4, and that gives us 2 moles per second. What have we just done? We've written the balance equation. Look at this. CH4, we have one of those, plus 2O2, we have 2 of those, goes to CO2, got one of those, plus 2H2O. We've got 2 of those. Now, however, we have oxygen in the product. So we're going to figure that one out. Oxygen, you want to do O2 last. Do O last. Okay, because it's the most complicated in the combustion reactions, because it shows up in a lot of different species. So we have coming out, we have water, CO2, O2, okay, and air. So this is known, N of O2 is known, N of CO2 is known. 0.21 is the moles of oxygen per mole of air, okay, and that gives us 5.2. Okay, now we just solve, and we have NO2 is 0.6. Okay, and we've already done the nitrogen balance. Okay, so we can add them up, all the stuff, to get the total moles out, and we have 2 plus 1 plus 0.6 plus 9.8 is equal to 13.4 moles per second. And you can calculate the mole fraction of each to get the concentration or composition. Okay, so if you're asked to tell the composition of the product, you should ideally put them into mole fractions. All right, let's try a calculation where we don't know the inlet conditions. The goal of this calculation is to examine the calculation of theoretical oxygen when there is CO in the product stream. Okay. So here's our flow chart given. Okay, so we have some moles of carbon monoxide and some moles of carbon dioxide. What is carbon monoxide? Carbon monoxide is because of incomplete combustion. Okay, so, but remember, when we calculate theoretical O2, we assume complete combustion. Okay, which means we ignore any information about the carbon monoxide only when we calculate the theoretical O2. Okay, so first let's write the balanced chemical reactions for this process. Because we have two products, we have two chemical reactions. Okay, if you remember the rule about independent chemical reactions, each time you have a species that hasn't shown up anywhere else, then that's going to be an independent chemical reaction. So you cannot write this as one reaction, because the number of moles of this going to CO is not the same as the number of moles of this going to the CO2. Why? They're independent. So you should not write them all into one chemical reaction. So now let's calculate the theoretical O2 for the process. All right, we have some of the exit flows. Let's determine those first. Okay, so we have 27 moles of dry gas, all right, So we multiply this by the mole fraction of methanol, which is CH3OH, okay? And that gives us 11.82 moles of methanol per hour. And we have CO2 coming out, so we get the total amount of CO2 coming out. And we have a mole fraction of CO, and that gives us the mole flow rate of CO coming out. Now what? What do we do next? If we look at our degree of freedom analysis, we can see the unknowns on the flow chart. Okay, we have 4 unknowns: N of F, N of the feed, N1, moles of air. Actually, this is written as moles of the molar flow rate of oxygen and the molar flow rate of nitrogen, which depends on the oxygen because they are not independent when it comes together in air. We don't know the molar flow rate of water out, and we also have some missing information in our flow chart about the oxygen coming out. Okay, so we have 3 independent atomic species minus 1 inert, and that gives us enough information. We don't need any degrees of conversion or anything like that. We also don't need to know what is the excess air because we can calculate that. We have enough information, knowing what we have in the products, to calculate the excess and theoretical air. Okay, so we can perform 4 balances. The carbon balance, okay, see that we have all of the carbons coming out. Okay, there's no unknown information about carbons coming out. So that means we can do a carbon balance and we can find out the amount of methanol coming in. We can do a hydrogen balance and get the moles of water going out. And we can do an oxygen balance, and we can do a nitrogen balance. Now here we have 2 equations with 2 unknowns, and we can solve those simultaneously, and we get that N1 moles of air in is 574 moles of O2 per hour, and X is equal to 0.822 moles of nitrogen per mole of dry gas. So now, let's calculate the theoretical oxygen. I invite you to turn off the video and try to do this on your own and see what you get, and see if it agrees with what I'm about to put on here. So, since we have completed all the balances, we know that the exit oxygen flow rate is 171 moles of O2 per hour. Is this the excess oxygen? No. This is the unreacted oxygen, not the excess oxygen. How do we calculate theoretical O2? Okay, here's our equation. All right, here I've only included the terms that we actually have. Theoretical O2 is going to be the number of moles of carbon in the fuel times 1 mole of O2 plus the number of moles of hydrogen minus the number of moles of oxygen. And we're going to calculate the theoretical O2. So there it is. Our theoretical O2 should be found as 444.9 moles of O2 per hour. And we calculated the actual O2 to be 574.3 moles. So our unreacted oxygen was 171. Our theoretical oxygen is 444.9. Our fed oxygen is 574. So let's calculate the excess O2 from the O2 fed minus the O2 theoretical divided by the O2 theoretical times 100%, and we should get 29.1%. Is that what you got? If it isn't what I got, did you try to use the information of carbon monoxide to calculate the theoretical oxygen? Because if you did, that's incorrect. We only use all the carbon goes to CO2 when we calculate theoretical oxygen. So once again, take this equation and put it somewhere where you can find it, because this is how you will always be calculating the theoretical oxygen in combustion reactions. So we do have a video quiz, and I'm going to have you do butane is burned with air. If 1 mole per second of butane is burned with 40% excess air, write the atomic balances for the process and determine the composition and flow rate of the furnace exhaust. Assume that no butane is in the exhaust, and assume that 90 mole percent of the carbon from the butane exhausts as CO2 and the balance as CO. Okay. So I'm giving you the mole fractions, and you are good to go. This will be posted as a video quiz.